Welcome back to Circuit Chats. Whether you're just joining us or following from the beginning, you're right on time because we're starting a new chapter. So, in this section, we'll take everything that we've learned previously about rectifiers, filters, and regulators, and we're gonna set it again into real-world applications from theory to full systems. And you're gonna see how each stage works together to deliver the power modern circuits that depend on. And this is what we can expect for this lecture. Key review of DC conversion stages, deep dives into line load regulation, practical tips on selecting regulators and smoothing components, and multi-sim simulations and ripple performance examples. And why does all these even matter? Well, if you want reliable microcontrollers, sensors, or analog gear, clean power isn't an option. It's essential. So you've seen diodes handle power and smooth out current, but did you know they're also great for protecting and reshaping signals? That's correct. That's correct. So today we're going to dive into diode limiters and clippers. These are some simple circuits with powerful controls. So let's start off with the clipper. What is a clipper or what is a limiter? So a diode limiter, it's also called a clipper. It's used to cut off or limit parts of a signal that go above or below a set voltage. So it's like placing a ceiling or a floor on a waveform, so it won't go past that. And why do we use one? Well, to protect components from overvoltage. So we don't want things getting damaged. We can also use them for signal conditioning and communication systems, and we can use them to create custom voltage levels in analog electronics. And how do they work? You're curious, I know. And so what happens is if the signal rises above a set threshold, and again, we'll look at the circuits in the next couple of slides so you see what's going on. But when it goes above that threshold, the diode conducts and clips the peak. So if it drops below a certain threshold, um, what's going to happen is the diode clips that too. And you can configure them to clip just the top part, just the bottom part, or clip both halves, the top and the bottom. The effect is that you're going to have an output voltage just a little bit more flattened on the top and the bottom, or wherever the diode cuts in, reducing the amplitude for one of the signal without distorting the rest of the signal. And where do we use these? Well, we use these in audio processing, RF, and communication receivers. We can also use these for digital input protection, and again, with sensors, we can use these with analog sensors and waveform shaping. So a good design tip before we move on is always add a reference voltage to the diode to customize the clipping level precisely. And we'll see what that circuit looks like in a few slides. So we introduced the idea of diode limiters or clippers. Now it's time to visualize the result. Let's look at these three basic clipping configurations and what they do to your waveform. So let's look at positive clipping and see what happens there. So a diode is placed to conduct only when the voltage exceeds a certain positive threshold. So that portion of the signal is chopped off or it's clipped. Right? The output is going to look like only the negative and lower half of the signal passes through. Right? All the positive peaks are flattened or they're clipped. Um, a good use case is to protect input pins on microcontrollers from high voltage spikes. Now let's go into the negative clipping. So what happens with the negative clipping? Again, this time the diode is flipped. We just turn it the other way. And it clips the negative half of the waveform when it falls below 0 volts in this case, or some set reference. And what the output is going to be that only the positive side of the waveform passes. The negative portions are removed, or those are flattened, just like the reverse of the first one. Um, what else? Where do we use these? Or when do we use this? Well, this would be used in cases where you need to block reverse current or you want to shape an audio signal. Now, the third image here, the dual clipping, where we clip both the top and the bottom. This is what happens. We have two diodes that are used in this case, one forward, one reverse. One clips the positive, the other clips the negative, and the output, only the middle portion of the waveform passes. So both top and bottom are chopped, leaving a nice little clean window. And you can use these when you're doing a signal thresholding, pulse shaping, or amplitude protection circuits. A good design tip is that you can clip to any level, not just 0, by adding a DC reference voltage in series with the diode, and we'll see what that looks like in an actual circuit. Okay, let's go ahead and continue with circuit chats. We're in the middle of signal shaping with diodes, and today we're taking a closer look at positive clipping. That's right. We're flattening waveforms to protect or reshape your signal. So here's what's going on. Take a diode like the 1N914, right? It's wired in parallel with a resistor across the output. So during the positive half of the input waveform, the diode becomes forward biased. It starts to conduct. This limits the voltage across the resistor to approximately zero point 0.7 volts, which is the diode's threshold. So that's what happens. Any voltage above 0.7 volts just gets clipped off and the output voltage flattens at that level. Now, during the negative half cycle, the diode is reverse biased. It acts like an open circuit, so the full negative voltage appears across the output, and that's limited only by R sub 2 and the rest of the network. So the resulting waveform here is that the positive peaks are flattened, the negative portions pass through, and the signal is clipped just on top. Hence, we call this positive clipping. Again, why use positive clipping? Again, to protect sensitive analog inputs from overvoltage, to shape waveforms in modulation, audio, or logic signal prepping, and to create precision clipping levels with reference diodes or things like Zener setups. And we'll learn what those are when we talk about special diodes next week. Okay, so we clip the peaks of a waveform to control over voltage. Now we're flipping things upside down, literally. We're going to look at negative clipping. So what's happening with this setup? The circuit is nearly identical to the positive clipper, except now the diode is reversed, right? So when the input goes positive, the diode becomes reverse bias. It behaves like an open circuit, and the signal passes unchanged across the resistor. The full positive waveform makes it through, in other words. When the input goes negative, the diode becomes forward biased. Then it conducts when the input drops below that negative zero point 0.7 volts for the silicon diode. So the voltage is clamped or flattened out there at that negative zero point 0.7 volts, just the opposite of what we discussed earlier. So the result's going to look like positive half passes fully, the negative half is clipped just below zero. And so you get a waveform with all the valleys flattened out. And why is this useful? Again, protecting analog circuits from negative voltage spikes, creating unipolar signals from AC, preconditioning waveforms before amplification or before digitization. And just like we talked about with the positive clipping, you can change the clipping level by adding a reference voltage in series with the diode. And we'll see some of those circuits coming up soon. This part of Circuit Chats, we're answering a question straight from the circuit bench. So what's the behavior of this dual diode limiter? So we have two diodes, opposite directions across a resistor, and let's go ahead and walk this through. Let's break down the circuit. So we got a 5-volt peak AC signal at 2 kilohertz. We have two diodes in parallel, but they're in opposite directions and both across a load resistor. So what this does is it clips in both directions. So during the positive half cycle, that 1N 4001G, which is D4, becomes forward biased. It conducts when the voltage exceeds approximately 0.7 volts. So the output is clipped at 0.7 volts, right? During the negative half cycle, you have a DN1, sorry, D2 1N914. That's the one that becomes forward biased in the negative cycle. And it conducts once the input drops below approximately negative 0.7 volts. So the output, therefore, is clipped at that negative 0.7 volts since it's in parallel with the resistor. So the final output waveform, the sine wave, gets flattened at the top and the bottom. And this is a classic dual clipper or a limiter circuit. So just to summarize the behavior, the limits between for this signal is going to be between 0.7 volts, positive 0.7 volts, and negative 0.7 volts. Anything outside this window is just chopped off. And this is a good symmetric clipper around 0 volts. And a good application for this would be input protection, amplitude control, signal shaping again, as we mentioned before. But again, we don't always have to clip at 0 volts. Flip waveforms at 0.7 volts with the plain diodes, and that's great for basic protection. But what if you want to clip at a signal something different? Let's say plus 2 volts or negative 3 volts or just any other level. That's where a biased limiters come in. So what is a biased limiter? So if you add a DC voltage source in series with the diode, we can shift the voltage at which that clipping starts. So instead of relying solely on the diode's 0.7 volts forward drop, we add this bias to raise that lower threshold. So let's look at the top circuit, the positive bias clipping. So here the diode is paired with a 2-volt DC source. It starts conducting only when the input exceeds that 2 volts plus the 0.7 volts, so 2.7 volts. And what happens is that it starts clipping anything above that. So the clipping starts at 2.7 volts. On the negative half of the waveform, that just remains untouched because remember it's reverse bias and all the output is shown across there. Um, so the output, what does it look like? Everything below 2.7 volts passes. Everything above that gets flattened. Now let's look at the bottom circuit, the negative bias clipping. So the diode is reversed. Again, with the same 2-volt DC biasing, clipping now happens at negative 2.7 volts. The positive signals flow freely, but the negative tips get chopped off. And what happens with the output? It looks like clipping occurs at a custom lower threshold. And why do we even want to use bias limiters? We've seen why we use limiters, but now we're using bias limiters. Let's say you have a customized voltage protection level. It's not at 0, or again, you want to shape the audio or RF signal. You can precondition. There's a bunch of stuff you can do with bias limiters uh, when you don't need something about 0, right? So a good design insight would be that if you're looking at the total clipping level, that's going to equal the bias voltage plus or minus the diode drop. Okay. All right, so that's it for this slide. I'll see you in the next one. In our last episode, we introduced bias limiters, a way to shift your clipping voltage up or down using a diode and a DC bias source. So let's look at the results of two circuits that show exactly how that behavior plays out. So the first one, circuit A, is a positive bias limiter, that's in the top left, and circuit B is a negative bias limiter, that's in the bottom left. So let's start off with the top. So you have an AC source, 10 volts peak, 2 kilohertz. The bias voltage is at plus 2 volts. And the diode is forward biased when the input exceeds 2 volts plus its 0.7 volts, giving us a total of 2.7 volts. All right, so if we look at what the resultant waveform is there at the top right, the input sine wave is in blue. As you can see that, the output waveform is in red, and it's clipped just above the 2.7 volts. So the rest of the waveform flows unchanged. And this is positive clipping with a defined threshold. Now, circuit B, negative bias limiter is at the bottom left. We got the same AC input. The bias voltage is 2 volts, but the diode is reversed in this case. So this time it conducts when the input is less than negative 2.7 volts. And the output waveform, which you see there in the bottom right, the negative half is clipped just below the negative 2.7 volts, and the positive half is untouched. And why this works is if you're moving the clipping window by combining the diode's threshold with a known voltage reference, and you can do this. But the big takeaway here would be that bias limiters, they allow for precise signal conditioning. Again, and they do the rest of the stuff that all limiters do. They'll protect circuits. You can create custom voltage windows, except for now you can actually shift them up or down. And you can use it to control waveform shape with just simple low-cost parts. So now we're going to go ahead and flip the approach. So far, we've been clipping waveforms, chopping off voltage peaks, but now we're going to learn how to shift the entire signal with a circuit called a clamper. And what is a clamper? A clamper doesn't cut your waveform. It adds or restores a DC level. So in other words, it shifts the whole signal up or down on the voltage axis without changing its shape. So think of it this way. If clipping sets a ceiling or a floor, clamping slides the whole waveform to a whole new level. So it works like this. You have a typical diode clamper circuit, in a diode, a capacitor, and often a resistor, and sometimes a DC bias source. And it responds during the part of the waveform cycle where you charge a capacitor, which then adds or subtracts DC voltage to shift that whole signal. So we got positive clampers, negative clampers. These are the types of clampers. Positive clampers shifts the waveform up, making the signal ride something, let's say above 0 volts. The negative clamper, right, shifts the waveform downward, and so it anchors the waveform something below 0 volts. So we also call these DC restorers or DC stabilizers, especially if you're working with like the older analog TV and audio systems. And why do we want to use clampers now? Well, let's say you need to restore lost DC in an AC coupled system. Maybe you want to prepare signals for rectification for conversion later, or you want to center a signal for analog to digital converters or waveform modulation, which we will discuss in a couple of courses from now. Okay, so we're going to explore the positive clamper here. It's, again, a diode-based circuit. It shifts an AC waveform upward, hence the name positive clamper, and it does this by adding a DC level. And let's look at how this works in a little bit more detail through this simulation. And what does it tell us? So what's in the circuit, right? The circuit's made up of a 5-volt peak AC source at 1 kilohertz. There's a 10 microfarad capacitor that's in series with the signal. We have a diode, a 1N4001G, pointing from ground toward the load. And we have a 10K ohm resistor across the output. So let's talk about how this works cycle by cycle. So the first cycle, let's talk about the negative cycle. The first negative half cycle, excuse me. The diode is forward biased, and the capacitor charges to the input, the peak input voltage, which is about 5 volts. But then on the next positive half cycle, the diode becomes reverse bias. A capacitor now acts like a DC source. It adds its stored voltage to the input signal, and the entire waveform is lifted up, shifting the negative peaks to something above 0 or higher, right? And the result is that your output waveform looks just like it did when it was the input. Your output looks just like the input, excuse me, but it's just shifted entirely above the 0 line or some voltage above that, right? So yeah. So what makes this a positive clamper? If you look at the graph there, the red versus blue, the blue is the input sine wave centered around 0, and then the red is the output. That's the wave that we've actually clamped. Um, so you can see it's not about 0 anymore. It's above something else. And that is it. And you can see that the whole DC is shifted upward. It's no longer on 0 volt DC. Some things you can use that positive clamping is good for: signal restoration for analog video, older analog video, peak detection circuits, and just level shifting for ADCs or logic inputs. Okay, now that you've seen what a positive clamper does on the waveform, let's go ahead and crack open the operation cycle by cycle again, and let's understand exactly how the capacitor, diode, and input work together to shift that waveform upward. So let's start all over with the negative half cycle. Again, during this time, we said the diode is forward biased. It acts like a short circuit, and the output voltage is 0 volts because the diode is directly clamping it to ground. Meanwhile, the capacitor is charging up. It charges to the peak input voltage minus that diode drop. So for a 5-volt input, capacitor charges to about 4.3 volts, right? And the next step would be the positive half cycle. So now the input goes positive. The diode is reverse bias. It acts like an open circuit. So the capacitor is just left to add its storage voltage to the input. And what you see at the output is 5-volt AC waveform that's now riding on top of that 4.3 volt DC bias. The result is that the waveform it gets shifted upward with all of it above 0 volts. And so the signal appears as AC with the DC offset. No distortion, just kind of like a relocation, a shifting upwards. And the takeaways for this slide are that the capacitor sets the DC shift level, the diode controls when charging happens, and the result is a waveform that stays entirely above the ground. And this matters because let's say you want to prevent signals from going negative, or you're aligning waveforms for an ADC inputs, or you're trying to restore lost DC in a communication system. Okay, we've talked about pushing a waveform upward with the positive clamper. Now let's go the other way. Let's go and talk about the negative clamper. What does that look like? What's that setup? So again, let's go ahead and keep the 5-volt peak sine wave, 1 kilohertz, the 10 microfarad capacitor in series, and we got the diode, the 1N4001G, that's connected in reverse compared to the positive clamper. And then we have a 10K load resistor. So again, let's do this one cycle by cycle, starting off with the positive cycle. So on the positive half cycle of the input, the diode is forward biased. It acts like a short circuit, and the capacitor charges to the positive peak, about 5 volts, right? During the negative cycle, the diode is now reverse biased. It turns off. The charge capacitor adds its voltage to the input. And what happens is that the waveform is shifted downward, right below that 0 volts. So the output, what it looks like, is a sine wave that stays intact, keeps the same shape, but it's just shifted down by some DC voltage, by some DC level. And in this case, it'll be negative 4.3 volts that it got shifted down. So why do we use negative clampers? So maybe, again, we want to align signal baselines for differential or bipolar inputs. Analog to digital converters are always a good use for this. And if, let's say, you want to stabilize DC levels in communication systems. So the amount of shift is controlled by the peak input minus the diode drop, just like with the positive clamper. Hey friends, and welcome back to Circuit Chat. So we're completing our tour of clampers by diving into the full operation of the negative clamper. If you've, again, ever needed to drop a waveform to a new baseline, this is how you do it. So let's start all over looking at the positive half cycle, right, when the capacitor is charging. Remember that the diode was forward biased. It's conducting and it's acting like a short as far as the diode is concerned. The capacitor charges quickly to the peak voltage minus that diode drop of 0.7 volts. So again, for the 5-volt signal, we're going and the 0.7 volt diode drop, we're going to have C charged to about 4.3 volts. Now, during this interval, the output voltage, again, taken across the diode, is going to be around 0.7 volts. Right? Continuing on with the next half cycle, the negative half cycle, this is the discharging and shifting. So now the input goes negative, the diode is reverse biased, so it turns off, and the capacitor acts like a battery. It acts like a source. So it adds its 4.3 volt charge to the incoming negative wave. And what's going to happen is the result's going to be that the entire AC waveform gets shifted downward. It rides on that new DC level of negative 4.3 volts. That 5-volt AC input becomes an AC waveform that's centered at something much lower instead of at 0. Right? So remember that clampers don't clip, they shift. That's it. Thank you very much. I'll see you in the next slide. All right, we're getting close to the end of this week's lesson, so let's continue. We're almost there toward the end. So we've seen diodes clip, clamp, rectify, regulate, but now we're going for something else, something big. It's time to use diodes and capacitors to do something a little wild when diodes go wild. So we're going to multiply voltage without a transformer. And so welcome to the world of what are called voltage multipliers. And so what is a voltage multiplier? What it sounds like. It's a circuit that uses a clever combination of clamping and rectifying actions, and it helps generate a DC output that's a multiple of the input AC peak voltage. Whew. Uh, Hopefully you got all that. And we use it for like high voltage, low current applications like CRT tubes. If you can remember any of your old TV tubes, like your old TVs. Electrostatic generators, high voltage bias circuits, and let's talk conceptually about how this works. So each stage consists of diodes and capacitors, and then the input AC signal charges the capacitors at different times. The voltage just adds up stage by stage into a larger DC output. So think of it like building a DC staircase from AC pulses. Um, then we have common types of multipliers: the half-wave voltage doubler, full-wave voltage doubler, the voltage tripler, the voltage tripler, and the voltage quadrupler, to name a few. And again, the half-wave voltage doubler, yeah, uses one phase of the input. The full-wave voltage doubler uses both phases, so you get a smoother output. The voltage tripler, it adds another stage for 3 times the voltage in. And then the voltage quadrupler, it keeps stacking stages, so you keep multiplying, right? But the reminder here is that the more stages you add, the higher the voltage, but inversely, the lower the current, right? So you increase the voltage, decrease the current. In order for power in to equal power out. Remember that conservation of energy, conservation of power from our physics icons, Isaac Newton. All right, so again, these aren't um, power devices, therefore generating high voltage and small currents. Right, for those of you following circuit chats, it's almost near the end of this lesson. We're going to go ahead and double down, literally. We're diving into half-wave voltage doublers. It's one of the simplest and smartest ways to get 2 times the peak voltage from your AC source just using 2 diodes and 2 capacitors. Remember what we said, the inverse relationship between increasing voltage or decreasing current. So remember that you always give up something. Okay, so what's a half wave voltage doubler? This circuit multiplies the peak voltage, V sub P, by 2 at the output. And how does it do this? Well, it works by charging one capacitor during one half cycle and then stacking that charge on top of the next cycle. So if we look at a step-by-step operation, starting off with the positive half cycle, D1 is forward bias. This allows current to flow. C1 charges up to voltage peak, which is approximately, oh, sorry, voltage peak minus 0.7 volts. And we don't have an actual voltage peak listed there, so no numbers. Um, what happens is that D2, I said, was reverse bias, no current flows into C2. C1 holds a charge like a tiny little battery. And again, during the negative cycle, D1 is now reverse bias, so that turns off. D2 is forward bias. That allows current to flow. So the AC input adds to C1's already stored voltage and discharges C2 to approximately 2 times voltage peak. And the output across C2 is at C2 is about 2 times VP minus the 1.4 volts to take into account the 2 diode drops. Across the 2 diodes. And the takeaway here is that no transformer is needed. So um, also, but yeah, no transformer is needed. It's ideal for low current, high voltage because we're stepping up the voltage, and there's no way around it. Current has to go down if voltage goes up. Uh, Law of power, it's conservation of power. There's no other way, not in this universe. All right. So again, each half cycle builds up to the output voltage, and then you get 2 times the voltage, but current handling again is limited. And some application of this again would be the CRT tubes, like your old TVs, photocopiers, the little gas igniters, and some electrostatic devices. Okay, so we've come to the end of our show here. So let's just recap. The last time we built a half wave voltage doubler. We're stepping it up to a more efficient version that uses both halves of the AC cycle. So we're going to introduce the full wave voltage doubler. And so you're asking, well, what is a full wave voltage doubler? This is a circuit that doubles the input peak voltage, just like the half wave version, but it charges both capacitors at the same time using the opposite half cycles of the AC waveform. So this is how it works, starting off with the positive half cycle. So in the positive half cycle, D1 is forward bias, and C1 charges to the voltage peak. D2 is reverse bias, so no current flows through that. C2 holds its previous charge, but then during the negative half cycle, D2 becomes forward bias, and C2 charges to the voltage peak. D1 is now reverse bias, so it just shuts off. And what the final output looks like is that the total output voltage is across both capacitors that are in series. So V out is going to equal to V sub P plus V sub P, which is going to give me 2 V sub P, right? 2 voltage peak. And this happens with every full AC cycle. And what this helps us, or what results with this type of circuit is you do get smoother charging, you get less ripple, you're utilizing both cycles. So those kind of make sense. And it's better than the half wave because it charges both capacitors every full cycle, not every other. The output is just more continuous and stable, and it's better suited for slightly higher current needs, but it's still kind of better for things like high voltage bias circuits for CRT tubes, laser printers, ionizers, and stuff like that. When you need something that has a very stable DC source, I can show you I'm gonna see if I can show you an example of using a really poor DC regulated source where I can try running something like a Raspberry Pi. And the Raspberry Pi needs a very consistent, good DC source. And if I don't put a good one on there, it'll indicate it. It'll show me that. Versus me using a power supply that puts out a very good DC source. So just because you buy one of those power supplies and it puts out the same voltage and current, and you think, well, this one's cheaper, the consistency of the cheaper one may not be as good as the more expensive one. It might have better regulation and better smoothing. You get what you pay for, in other words. But if you're just like charging a circuit, yeah, those things don't really matter too much. But if you're powering a circuit, like I'm powering a mini PC, and so I'm powering the circuit, I'm not charging batteries and running it off the battery. actually powering the mini PC, it needs a very stable power source. So it would be different. Okay, that's it for this week's lectures. I want to thank you very much for tuning in to uh, what did I call this thing? Circuit chats. Circuit chats. And I will see you next time when we talk about diodes and special purpose diodes.